Alrighty, so today we're going to go ahead and talk about symmetry on shapes. So again, different types of symmetry that we can see with geometric shapes. A figure has symmetry if there's an isometry, which means that the shape stays the same thing. So say you take your body and you move it over here, you still the same thing, you just flipped around. You just moved. Same thing when you spin in a circle. You spin 180 degrees. I am still myself, just backwards. So again, it's a figure has symmetry if there's an isometry that maps the figure onto itself. So again, isometry is something that stays the same. If it is a reflection, then it's called reflectional or line symmetry. So for example, if you cut a butterfly in half, you have reflectional or line symmetry down the middle. Same thing with this picture of a mountain. If you are looking at the water line to the actual, like the water part to the actual mountains has a reflectional symmetry. Okay, so it is possible for a figure to have more than one line of symmetry. In this hexagon, we have symmetry on the red line, so there's 1. We see the light blue line, so that's 2. Purple, 3. Orange is 4. Light green is 5. Blue is 6. And then if we look again, we're back at that red line. So this hexagon has, come on pens, 6 lines of symmetry. Well, how many lines does a snowflake have? Okay, well we can put 1 here. So that's 1. We can put 1 here. So that's 2. We can put 1 here. So that's 3. We can cut it in the middle like so. So that's 4. And we can cut it here. So that's 5. And we can cut it here. So that's 6. So this snowflake has 6 different lines of symmetry. Some other types of symmetry are if you take a diamond and cut it in half. You can cut it long ways, and you can cut it across. This cross-like shape in half long ways, short ways, and the diagonal. And then you can cut a starfish in half. Several ways. So let's go ahead and determine how many lines of symmetry each picture has. We're going to go ahead and draw these lines. So if you're taking a look at that little coconut head dude, that guy just has 1 line of symmetry right down the middle. My X has a line of symmetry here, has a line of symmetry here, and it also has symmetry on each of the diagonals, because if you were to cut those in half, you'd still fold over and be able to create the same looking thing on both sides. My square, I can cut down the middle, and in the diagonals. The letter B, however, that can only be cut this way. I'm only going to be able to fold it in on itself. My heart, if you remember from drawing these in grade school, we fold that piece of paper in half, then draw the half of the heart, and then we cut it out, and you have a whole heart. And then likewise with this mask, I can only cut it down the middle. So those last only have 1 line of symmetry. A figure has rotational symmetry if it can rotate 180 degrees or less and land up almost in the exact same spot that it started in. So if I make a triangle, I'm going to try this as best I can. It didn't really work out in class too well, just because I couldn't get it to sit in the same spot. If I rotate this triangle, doesn't it look like the one that I just created, or I just drew. If I put, what I'm essentially doing is putting a finger in the middle, so on your finger on your computer, and follow me as I rotate it. Granted, that dot I know is not exactly in the middle. My shape is still staying, isn't it? It's still staying that triangle. It's essentially in the same spot as it was before I'd even started rotating it. If I go all the way back, again, it's back in its same spot. So this triangle has rotational symmetry because I can put a point in the middle and I can spin it. I put my lesson plan book and I stuck it here. I can spin that, and at 180 degrees, it'll get back to the same size. So when I'm dealing with this triangle, I want to determine how many degrees of rotational symmetry this has. So think about it. When you spin, what shape do you typically spin in? Well, you spin in a circle. When you spin in a circle, you have 360 degrees to play around with because everything has to add up to that 360. Okay, so if I have 360 degrees and I'm spinning this triangle around, how many points does my triangle have? Well, it has 3. There's a point here, there's a point here, and there's a point over here. So what I'm going to do with that 360 is I'm going to divide it by those 3 vertices as we just talked about. So when I take 360 divided by 3, I get 120. An equilateral triangle will rotate 120 degrees to get from one vertex to the next vertex. And I just showed you mathematically. All right, so let's look at some examples of rotational symmetry. So this recycling, there, I couldn't think of the word. This recycling sign can be rotated. If I flip my shape, I get to the same shape again. And I get to the same shape again. And I get back to the original. Kind of. So that shape can be rotated. Now this is like a triangle. It has 3 things. So this one can be rotated 120 degrees. Let's take a look at my yin yang. If I just rotate it like this, is my shape the same as when I started? No, but what happens when I go even more? Granted, someone pointed out in class, but the colors aren't in the same spot. You're correct. The colors aren't necessarily in the same spot, but the shape itself, if I were to take out that black and the black parts and just leave everything white minus the outline, this shape has rotational symmetry now of 180 degrees. The reason being is I couldn't do it until I had flipped it around. So if you remember, straight lines, flips are 180 degrees. So this guy has 180 degree rotational symmetry. I'm going to put him back right. Maybe. All right, this pinwheel. You notice, if I just flip it one little turn, I'm back to the same shape I already was at. Now, if it has 4 points, because I have 1 point, 2 point, 3 points, 4 points, I'm going to take 360, divide that by 4, which gives me 90 degrees. Good job. So that pinwheel has rotational symmetry of 90 degrees. This weird hazmat-y kind of looking symbol. Oh, those are connected together. I'm going to spin both of them at the same time. Ignore this one for a moment. I spin that guy. Granted, he's not in the exact same spot because they're connected together. But my shape is staying the same, isn't it? We're imagining it spinning on that circle there in the middle. Gonna have to cut that later and fix that. Because of that, he has rotational symmetry there at that point in the middle. And this is very similar to a triangle. So this has rotational symmetry of 120 degrees. What shape does this guy in the middle look like it has? Right, it's got 4 spots. I can spin it like my pinwheel. This one's going to be 90. Now, I know this one is kind of hard to see on your paper. If I blow it up a little bit, it already kind of gives you the answer. If you take a look at the flower, it makes a semi-triangle between the petals here. So this flower also has rotational symmetry of 120 degrees. Okay, judging from the appearance, tell whether the figure at the right has rotational symmetry or point symmetry or both. Well, is there any way that I could cut this guy? Can I cut him that way and fold him in half? Will he be the same on both sides? Nope. Alright, what about this way? Can I cut him in half and still be the same shape? Fold him in half? Fold him like a piece of paper? Hot dog style? Alright, so this guy does not have any line symmetry, so that means he must have rotational symmetry or point symmetry. And then let's figure out how many degrees I can spin him. So if I spin him 90 degrees, is he the same spot? But if I spin it 180 degrees, doesn't it look the same as when I started? So this guy has a point symmetry or rotational symmetry. Of 180 degrees. Alright, last one. Judging from the appearance, does V or H have rotational symmetry? If so, give the angle of rotation. Well, let's take a look at... That's a weird number. Let's look at this V. If I spin him, do they look the same? Do they look the same? And when I deal with rotational symmetry, I can't go more than 180 degrees. Well, I'm at my 180 degree mark, so I can't be V. But what about the big capital H? Can I spin him? Well, it's 90. Oh, hey, look, it's H upside down, but it's still H. So my H does at 180 degrees again. Okay, so reflectional line or line symmetry is a mirror image, so that's where it can be folded. There. That means it can be folded in half. Same on each side. Rotational symmetry is something I can spin. I'll have to do a bad example. Like my notebook. I can spin it. Alright, that's all I have for you today.